Welcome back. So, in this video lecture, we are going to look at what is known as Derjaguin approximation and DLVO forces of interactions, right? In previous lecture, we looked at the electrostatic repulsive forces between two, when between two planar interface, planar surface, right? We considered the overlapping of double layer between two planar surface, right? So, but in this video lecture, we are going to look at the electrostatic repulsive forces of interaction between two spherical double layer, right? So, when the electrical double layer overlap, electrical double layer of two spherical particle overlap, how will the electrostatic repulsive force be? That is exactly what, how will be the electrostatic repulsive force of attraction, electrostatic force of repulsion between two spherical particle is what we are going to look at in this video lecture. Apart from that, we will also see what is known as the DLVO forces of interactions, right? So, DLVO forces of interaction is nothing but sum total of the van der Waals force of attraction and the electrostatic repulsion, right. So, a combination of these two is what nothing but the DLVO forces of interactions. So, we are going to look at these two things in detail in this video lecture. Let us begin. So, let us first start with the interaction between the planar surface that we obtained, the derivation that we saw in the previous video. So, this is nothing but the disjoining pressure that we obtained between two planar surface, right. So, if you look at this equation, so this is as a function of separation distance, right. Rest everything is constant. So, psi is the surface potential here, okay. That can be determined using using the zeta sizer. If you know the zeta potential, maybe we can relate that to be a surface potential, and let us see, you will see those things later. But now we assume that this equation is as a function of separation distance, okay. Now, from the disjoining pressure, it is easy for us to calculate the electrical double layer forces, right, between two planar surface. So, for that what we have to do is we have to simply multiply this equation with effective area, right. That is exactly what we have done. So, pressure so disjoining pressure multiplied by effective area will be your force due to electrical double layer, overlap of electrical double layer. So, this is very clear. So, here only one change we made was we just multiplied this disjoining pressure equation with respect to area, right. So, this is very clear, right. This is for the two planar surface. Now, question comes, let us say if you want to use estimate or calculate the pairwise interaction between spherical double layers. So, assume that you have a spherical particle, and if you want to calculate the pairwise interaction between two spherical particle, how will you obtain the total energy, right, of the two spherical particles? So, that is the question that we are asking. Now, why we should do? We should know, because more often than not, you will be dealing with colloidal particles in various applications, right. So, sometime you may be working with the spherical particles, right, although you will also be working with the non-spherical particles, but it is first thing, it is easy to to understand first for the spherical particle case, then maybe you can develop on your own for non-spherical case also. So, spherical case is very the simplified one, and it is generalized case. So, we will first look at how we can calculate the interaction between the spherical double layer, right. So for that, so the question that we are asking is, can we use this equation as it is for spherical double layer? The answer is no, because you can't use it as it is not one on one because of the curvature effect. Okay. In the case of spherical, in the case of planar surface, remember when we tried to calculate for a planar surface, what we assumed was, I mean, we used the principle of superposition theorem, right? Okay, to calculate what is the potential at the midpoint. So we know the midpoint, that is nothing but psi m. So we use principle of superposition to understand what is psi m. So psi m is nothing but sum total of the psi 1 and psi 2, right? The potential acting on the plate 1 and plate 2. So this principle we have used, and then we obtain this equation. Now question comes, can we use similar strategy here? The answer is exact, I mean precisely, I mean you can't say straight away yes, because there is going to be variation due to the curvature effect. Say for example, if I draw the the separation distance, you can see that there is not one single separation distance, and it is varying for uh, along the curved surface, right. So you can see that at some midpoint, at some point, the minimum distance, the separation distance is minimum. At in in other case, the separation distance is also maximum. So what is the the difference here? If you ask me, the difference here is the molecule which are placed very at the close proximity between the two. Let's say this point, if you look at, so they have the advantage, right, because they will interact much more than the molecule sitting at the corner here. Okay. It is so the interaction will be more dominant here, and then rather, I mean than the molecule sitting on the other side, right. So this is the problem here. Because of this, you can't use this the approach that we used earlier as such here, as it is here. So we need to do make some strategy for that, right, how to overcome that the issue, right. So that is exactly what we are going to look at here. So you can see that because this that is at the close proximity, the molecules get more advantage, right, than the than between, I mean the molecules which are far away from each other, right. So this is the issue, right. So how do we deal with? There is something called Derjaguin approximation, proposed by a Russian scientist in 19th century. So this approximation mathematically help us calculate the interaction between the spherical double layer easily, okay, by just modifying the problem, right, according to the equation that we know already. For example, this is the equation that we know already. Okay, so this is for the planar surface, or you can say flat surface. Okay, now we are going to use this equation as it is, right, that is in the form of pi of x. So why it is pi of x? Here we are, x is also variable, the separation distance here is variable. So that is exactly what we are going to do. So we are representing in terms of pi of x. Now question is, how we can use this equation as it is and then use this for this spherical double layer. So it's very simple. What Derjaguin did is, he actually this curvatures, so curved surfaces, he broke into several tiny flat surface. For example, imagine you have infinitesimally small or very tiny flat surface, right. So there are infinite number of such plates. Okay, when you cut this curved surface into infinite number of flat plate or flat disc, okay, and then if you calculate for each the individual flat plate which is very small, right, which is very tiny, infinitesimally small, that you can for that you can use this equation, because this is considered to be a flat surface now. Okay, because when you consider this as a flat surface, the for each and every small tiny flat surface, you can say that the separation distance is not varying, right, as a function of the curvature, due to curvature, right, because this is considered to be flat surface. You can so more precisely you can call it as a flat disk, because this is coming out of the curved surface. You can imagine this is a flat disk. Okay, and the step change is nothing but dr here, right. The step change that you make here, that is the dr, and so it's a flat disk. You have flat disk with the radius r, and dr is the you know the that small change, that that small tiny flat plate, right. So that is exactly what you are going to do here. So the idea is, the strategy is very simple. I know what is the equation for flat plate. Now I am going to consider this curvature as infinite number of flat plate. Okay, I know for one flat plate, okay, which is very small, and then I will integrate that for over decide a large area, decide area. Then I will be able to get the total interaction of the spherical particle. So that is the idea, that is the strategy Derjaguin has used. So what we will do is, we have to just use this equation as it is, that is pi of x multiplied by dA. dA will be because we consider is a flat plate, although it is a flat plate, because it is cut down from the spherical or the curved surface. You can imagine as a flat disk itself, right, flat disk itself. So this area will be 2 pi r dr. So this is somewhere you should note down, this is nothing but 2 pi r dr. Okay, and so imagine you have very small tiny flat disk, right. So when I say it is infinitesimally small, you can take it into a continuum domain, which means that it is no longer a discrete function, it is a continuous function. So for that case, you can use very well use this integration, going from one lower limit to the upper limit. So you can go from 0 to any desired area. When you do that, you are actually taking into account the interaction of all the molecule present within this projected area. So remember, we are considering only this part of the curved surface, right, because this part is actually out of the projected area, right. Only this part of the area will be curved surface, will be directly related to each other, because the molecules see them see them each other, whereas from this point you can see that they are away from the projected area. So we are considering this particular curved surface, and you further break down this curved surface into several tiny flat disks, and then you relate one flat disk between two flat disks. The equation that is already known, that we are using again here, multiply by dA, and integrating it from one limit to another limit will give you total interaction between the two spherical particles. So that is the strategy we are using. Now we need to do some geometric naming, right. We need to find out some geometric relation. For example, the x here is also nothing but h. H is the minimum separation distance, plus 2y. Y is the distance between the one end to this one, right. So this is so you draw a line between one end from here to another end. Okay, so this is basically what we talk about. And if I extrapolate this two thing, this is my y, right. And similar way, if I extrapolate these two thing, this is my y. So x is nothing but, in this case x is nothing but h plus 2y. Okay, we will see how it will be useful, how this geometric relation will be useful. Then we know, look at this triangle, gray triangle. Okay, this is a perfect gray triangle. If you look at this triangle, you can use the triangular property, that is AC square equal to AB square plus BC square property that we know, this relation that we know already. If you use this relation, you can easily calculate what is the R square. So, this one is R square, that is what I have put here, which is nothing but this entire thing is R, right? This entire thing is R radius, but this part is R minus Y, right? That is what exactly I have mentioned. So, R minus Y square plus R square. So, this is your R square, right? This part is R square, R, right? So, then you can use this triangular property, Pythagorean theorem. You can use this Pythagorean theorem on the great triangle. If you use Pythagorean theorem, you can simply get this relation, right? We will see why this is useful for us. Now, all we need to do is we need to get dA, change in area, which is 2 pi r dr, but this is not desirable for us. What we need is, we want to convert this r dr, because r dr is unknown for us, right? It is not easy to always get this r dr. Now, what we can do is, we can convert this r dr into the r dx, which means the radius of the particle is capital R, dx is, so x is the separation distance, right? So, as a function of x, how you can calculate the area. So, the change in area, that is exactly what we will have to do. So, that is the modification we have to do now. That is why this geometric relation is going to be very useful for us, right? That is where it is going to be useful for us. So, let us first start with, first let us understand what is the relation that we from the triangular we got. So, let us use that. So, we know from the triangular property, r square is equal to small r square plus r minus y square, okay. Now, we want something in terms of small r. So, I will keep r square, which is nothing but r square minus r minus y square. So, all I need is, I need to differentiate this r with respect to y. So, 2r, I will say 2r dr by dy is nothing but, it will be 2 into r minus y, okay, right, because minus is here outside, and when you differentiate, this will be 2 into r minus y into minus 1, that will be 2 into r minus y. So, remember, we are going to make an assumption such that it is also it is also valid in many cases. So, the capital R is very larger than the y. If you make this assumption, it is also true in many cases, right? Because the length scale of the radius will be larger than the dimension of y, right? So, in that case, you can ignore this y. So, you can simply keep only the 2r. In this case, you will have 2r, okay, only, or you can say 2r dr is nothing but 2 capital R dy. So, this is exactly what we have, these relations we have. Now, but still I want to convert this y into x. So, how do I do? So, what we know in terms of x, the another geometric relations that we know is nothing but x is nothing but h plus 2y. This is what we know, right? In this case, so what we will do is we substitute. So, we know what is in this case, what is dx then? Dx will be, okay, 2 into dy, or dy will be simply dx by 2, okay. So, dy will be dx by 2. So, if I substitute this one here, my dy will be dx by 2. So, simply it will be pi capital R dx. So, I am now able to convert this 2 pi r dr into pi r dx, okay. My job is done now. Now, I have to just go back here. I have to substitute this dA and simply integrate it, right? That is exactly what we need to do. So, if I do that, so what I will be getting? So, I have this equation, that is pi of x dA. Why we are writing pi of x? Because now this equation is going to be in x, right? So, pi of x in dA. So, if I substitute that here, what is constant here is pi and capital R I can keep outside the integral, and pi of x dx can be kept inside the integral. If I integrate this, I will be simply getting, remember this entire part is constant, I am calling it as Z, right, capital Z. So, capital Z is outside, e power minus kx dx is what we have to integrate. Remember, your lower limit will be minimum separation distance, right. This is your overlap of electrical double layer, right. This is your minimum separation distance, that is h here. It is going to be h from, so it is from minimum separation distance to far away, up to infinite, I mean up to infinity. So, you can keep this integral limits. So, then if you integrate it, you get this equation, that is pi r. So, if we integrate this one, so basically what we have to do is we have to integrate this h into infinity e power minus kx, right. So, kx dx. So, if you integrate this, you will basically get e power minus kx integral, so h to infinity, okay, by minus k is there. So, e power minus infinity is 0 minus the lower limit when you apply e power minus kh by, so this will be anyway plus, it will become plus. So, you will have e power minus kh by simply k. So, that is exactly what you have. So, k you can also write it as k inverse. So, k inverse is the screening length, that is exactly what we have obtained here also. So, this is the equation for electrical double layer force, okay. But you can also convert this electrical double layer force into energy, right, repulsive energy. For that what you have to do is, that if you can also call it as d pi by dh, okay. In this case h is the minimum separation distance, right, or you can also integrate it with respect to dh. Say for example, I can also convert derive from this, get the information in terms of energy by simply we know f of h into dh, right. So, by doing so, I can simply get the equation in terms of energy, that is going to be pi equal to 0 to pi, right. So, in this way also I can get the equation in terms of energy, that is exactly what I am going to do here. Now, the limit here can be between 0 to pi. Why we are keeping minus here? Because this is negative gradient, which means that the slope is negative. It indicates that the pi, that is interactive energy, energy decreases as h increases. So, if you go away far away from minimum separation distance, right. So, if you go from minimum separation distance, right, as h increases, right, okay, your pi actually decreases. So, this is what exactly it means, or else if you plot between pi and h, you get is, what you get is the negative slope, right, the slope value is negative. So, that is exactly what it means, okay. So, minus d pi by dh, and if you integrate this one here, you will get finally this equation, that is pi r k power minus 2, which is now you can also keep in the denominator as k square. Remember, this equation now is the unit of this equation is now in terms of joule. You can check that the unit of z, is nothing but kb is joule per Kelvin, temperature is Kelvin, right, and you will get joule. This one is moles per meter cube, number of moles per meter cube, number of molecules per meter cube, okay. So, which means that ultimately you will have joule per meter cube here, okay, and multiply by, you will have the k inverse, right. So, k minus 2, this is actually meter squared, okay, and you also have r, which is meter. So, you will get both this term related to meter cancels out from numerator and denominator. What you will get is the unit of joule only. So, what you get is the energy equation, which is in the unit of joule. That is exactly what we obtained here. It is more, it is compact equation. So, it is same as your interaction between the planar double layer, whereas here you have the additional term like k minus 2, right. So, this is there already. So, otherwise rest of the thing is pretty same, right? Right. So now what we have to do is we have to look at what is known as the DLVO force. You know that DLVO force is nothing but sum total of electrostatic repulsive plus van der Waals attractive force. Okay. So that is exactly what we have written here. This is the electrostatic repulsive force just now we obtained for a spherical double layer, and for two spherical sphere of same radius, right? Same radius. The here R1, this is R1, right? R1 and R2. So here R1 equal to R2. For this case, the equation for the van der Waals, equation for this case is AR by total H. Okay, you can verify this equation by referring to the table 10.4, right? Using this, in this textbook. Okay, you can see this equation for different configuration. It is given in the form of table, and this one is for the spherical particle having same radius, right? So this equation is obtained. This is for the van der Waals equation, van der Waals attractive energy, attractive, van der Waals energy, right, between two spherical particle, and this one is electrostatic repulsive energy between two spherical particle. The sum total of this is going to be your DLVO. If you plot this on as a function of distance, you will get something like this. Okay, you will get something. Okay, yeah. So maybe I have not drawn. Maybe so this is something. So you can also verify the textbook. So this is actually this is a small fluctuation here. This is the secondary minima. Okay, this is due to weak dipolar interaction, right? And this one is the primary maxima. This is the barrier, right? A repulsive barrier, and this one is the primary minima. Okay, so this is due to the van der Waals term, and this is due to the repulsive term, and this one is due to the bond repulsion, right? So when you plot this DLVO, this equation, okay, as a function of the H distance, separation distance, you will basically obtain a profile something like this, the way I have shown here. Okay, for more details you can refer to this textbook. Okay, and I think you can also refer to this table for other configurations as well. Okay, yeah, so we will stop here. We will continue from the next lecture. Thank you.